Welcome to Dr. Boxy Teaches Electromagnetism. So what is electricity and what is magnetism? And why are they considered to be one and the same topic in physics known as electromagnetism? If you think about it, electricity is related to what happens when we charge our phones, for instance, while magnetism has to do with what happens when we put certain metals on our fridge doors. There doesn't seem to be an obvious relation between them, but it turns out they are deeply and intimately connected. In this course, we will study electricity, magnetism, and the relations between them. This covers a huge range of physical phenomena we encounter in our daily lives, going from light bulbs all the way to MRI machines, and from rainbows all the way to the neurons in our brains. By the end of the course, you will have a deep understanding of the underlying physics of all these phenomena. This is a course that is typically taught in a second year of an undergraduate physics program at university, and because of that, there are some prerequisites to taking it, though probably not as many as you might think. From a mathematics point of view, you need to have a high school level of trigonometry and calculus, and you need to be able to calculate the determinant of a 3x3 matrix. From a physics point of view, you need to have taken a first course in classical mechanics. I will use concepts like energy, momentum, force, acceleration, and you need to be comfortable with these. If you have taken a course on classical mechanics before, you should be completely fine. The course is based on the book Introduction to Electrodynamics by D.J. Griffiths. It is one of the best textbooks on physics I've ever read. It's incredibly well explained and I cannot recommend it highly enough. We will cover the full book in this course, but because it is such a huge topic, I've decided to divide the course into two series of lectures. In the first series, we will study the necessary mathematics and physics to arrive at the four cute equations you see written now next to me. These are known as the Maxwell equations, and they summarize virtually everything we know about electricity and magnetism. By the end of the first series, you will understand what these symbols represent, what they mean, and how to work with them. In the second series, we will start from these equations to study topics like electromagnetic waves, electromagnetic radiation, some conservation laws, and even the special theory of relativity. This theory of relativity was actually born in the early 20th century out of an attempt to resolve a conflict that existed between these four equations on the one hand and Newton's laws of motion on the other hand. We will get to that. For now, in the first couple of clips, we will study some mathematical background necessary to actually start our study of electricity and magnetism. And in this very first clip, we will look at vectors. What are they? How do we work with them? And why do we need them in the first place? So let us get started. So why do we need vectors? Imagine you walk a distance of 3 meters upward, and then you walk an additional 4 meters to the right. The total distance you've traveled is of course 7 meters. But if I asked you not what the distance is that you've traveled, but how far the starting point is from your endpoint, the answer would not be 7 meters. It's only 5 because the distance is the hypotenuse of a right triangle. What we want to do is to develop some mathematical formalism that allows us to also take directions into account. Anytime we encounter in physics some quantity that has a direction, we will need vectors to describe it. And that is the case with forces, for instance. If you push an object, you need to know not only how hard you're pushing, but also in what direction you're pushing it. And it will turn out that we will need it to describe electric and magnetic fields. And in this specific sense that we have on this slide, 3 plus 4 could be equal to 5. And what we want to do is to develop the mathematics that will allow us to do this. So, what is a vector? A vector is simply an arrow. I call this vector A, and to emphasize the fact that it's a vector, I drew an arrow on top of it. When I draw it by hand, when I write it by hand, I will just put a bar on top of it. Now, a vector is characterized by its direction on the one hand and its magnitude or length on the other. That means that if I take the vector A and I move it around, it remains the same vector. I'm allowed to take a vector and move it around as long as I don't change its direction or its length. The length of the vector will be denoted in one of two ways. Either I will write the vector A with absolute value signs around it, or simply by the letter A without a bar on top. Note that the length of an object is always a non-negative number. It's meaningless to say that an object has a negative length. You might have noticed that I have the endearing handwriting of a 7-year-old. I will do my very best to be as clear as possible, but if anything is unclear, please don't hesitate to contact me, ask me questions. I'm happy to answer any question you might have. So we know what a vector is. There is also something known as a unit vector. A unit vector is simply, by definition, a vector of length 1. Any vector of length 1 is a unit vector. And to emphasize the fact that it is a unit vector, I will put a hat on top of the name instead of the arrow. So we know what vectors are, but what can we do with them? In the context of vector algebra, there are a number of operations we define on vectors. And the first one is known as vector addition, and we will write it as A plus B. Then there are 3 different operations, all known as multiplication, all different from each other. The first kind of multiplication is known as the multiplication of a vector by a scalar. The word scalar is simply a fancy word for the word number. So all we're doing is we're multiplying a vector by a number, let's say 7b. A second kind of multiplication is known as the dot product, and we will write it as A dot B. And the third kind of multiplication is known as the cross product, and it will be written as A cross B. I want to point out the fact that with numbers, whether I multiply 2 by 7 and write it with a cross, or I multiply the same 2 by 7 but I write it with a dot, they mean exactly the same thing. For vectors, the dot and the cross have a completely different meaning. They are unrelated. We will see what each of them means and when to use which one, but keep that in mind because that's a mistake that I see a lot of students doing in the beginning. So let's go through each of these operations one by one. The first operation is vector addition. We take 2 vectors A and B. What do we mean by A plus B? Well, take the vector A and move B such that its starting point coincides with the end point of A. We put them tip to tail. The vector that then goes from the starting point of A to the end point of B, so the vector that closes a triangle, is defined to be the vector A plus B. Note that because of this definition, the magnitude of A plus B is not equal to the magnitude of A plus that of B. Simply because in general it's not true that in a triangle one side is equal in length to the sum of the 2 other sides. Now with numbers we know that the order of addition does not matter. Whether we add 2 and 4 or we add 4 and 2, we get exactly the same result. The question is that true for vectors? Well, what we will do is we will look now at B plus A. So we take B first and we move A such that its starting point coincides with the end point of B, and we close a triangle going from the starting point of B to the end point of A, we get B plus A. And the 2 light blue vectors are indeed equal to each other. This turns out to be a general property of vector addition. Whether we add A plus B or B plus A, we get exactly the same vector. So this is vector addition. The first kind of multiplication of vectors is known as the multiplication of a vector by a scalar. Again, scalar just means number. So we take a vector B and we multiply it by a number, let's say the number 3. What we get is a vector that has the same direction as B and is simply 3 times as long. Now multiplying the vector by a scalar doesn't need to make it longer, it can also shorten it. If I multiply B by the number 1/2, I get a vector that is half as long. We also define the multiplication of a vector by a negative number, minus 2b for instance, is a vector that is twice as long as b, and the minus sign flips the arrow around. It reverses the orientation of the arrow. So the vector minus b, for instance, which is simply the number minus 1 times b, is a vector that is the same length as b and just points in the opposite direction. This multiplication of a vector by a scalar has an important property known as distributivity. It says the following: take some arbitrary number, some arbitrary scalar lambda, and we take 2 vectors a and b. The property says that if we add a and b and we multiply this resulting vector by the number lambda, or we multiply each of the vectors separately by the number lambda and then add them, we get exactly the same result. Basically what it says is that we are allowed to open up brackets when it involves multiplication of vectors by scalars. So this is the concept of multiplication of a vector by a scalar. Using it, we can define another algebraic operations on vectors known as vector subtraction. We take two vectors again, a and b. What do we mean by a minus b? Well, we just define it as a plus the vector minus b. So we know that the vector minus b is the vector b and flip the arrow around, and now we add a and minus b to get, you take a and you put minus b such that the starting point of minus b coincides with the end point of a, and you close the triangle. This is the vector a minus b by definition. There is another way of thinking about the vector a minus b, and you can see that by drawing a and b such that their starting points coincide. My claim is that the vector that goes from the end point of b to the end point of a, the one that I called c here, is also equal to a minus b. Well, first of all, purely visually, those two vectors indeed look the same, but they are the same, and the way to see that is to look at what happens in the drawing on the right if I add the vectors b and c. Note that if I add those two vectors, by our definition of addition, what we get is the vector a. But if we now subtract the vector b on both sides of this equation, we get exactly what we were looking for. C then equals a minus b. So either way of thinking about a minus b, either by putting a and minus b tip to tail, or having a and b start at the same position and then closing the triangle going from the end of b to the end of a, you get exactly the same vector. That is the definition of vector subtraction. Now, the second kind of multiplication between vectors is known as the dot product, a dot b. We define it in the following way. We take the magnitude of a times the magnitude of b times the cosine of the angle between a and b. Now, what do we mean by the angle between a and b? Take the two vectors a and b and move them such that their starting points coincide. The angle between them is the angle alpha. By definition, it is always the inner angle, and because it is the inner angle, it always lies between 0 and 180 degrees. Notice that a dot b, which is ab cosine alpha, is a number, so the result itself is a number, a scalar, and therefore the dot product is sometimes also called the scalar product. Now, we know what it means, what it is by definition, mathematically, but what does it actually represent? To understand that, let's take some unit vector c in some random direction, and what I want to do is to calculate b dot c hat. So I put b at the beginning of c hat, the angle between them I call it beta, and I want to calculate b dot c hat. Now by definition that is the magnitude of b times the magnitude of c hat, which is 1 because c hat is a unit vector, times the cosine of beta. The question is, what does this mean? What is b cosine beta? I draw the line on which c hat lies, so the dashed line I drew now. From the endpoint of b, I project a line perpendicular to that line, the one in blue now, and note that I created a right triangle this way. One of the sides of the triangle, the left one, the one on the dashed line, I called it x. Because we have a right triangle, we know that the cosine of beta can be written as the adjacent side divided by the hypotenuse. The adjacent side is x, the hypotenuse is b, so we get that cosine beta is x divided by b, which is equivalent to saying that x equals b cosine beta. Note that that is exactly what we found for b dot c hat. So b dot c hat is the blue line. It is the projection of b on the line on which c hat lies. Anytime you have projections of vectors onto directions in physics or in mathematics, you will always have to work with dot products. So what are the properties of the dot product? Well, the first one is that a dot b and b dot a are the same. This follows directly from the definition. A dot b is defined as the magnitude of a times that of b times the cosine of the alpha between them. And b dot a is the magnitude of b times that of a times the cosine of the angle between them. And both magnitudes and the angle did not change, so we get twice the same result. A second property is again a form of distributivity. It says that once again we are allowed to open up brackets when there are dot products involved. A third property is that the dot product of two vectors is zero if and only if they are perpendicular. This again follows directly from the definition. A dot b is ab cosine alpha. The only way for this to be zero is assuming that both vectors are not zero themselves. The only way for this to be zero is for the cosine to be zero, and that is the case only when alpha is 90 degrees, so when they are perpendicular. A fourth property is that the dot product of a vector with itself is equal to the square of its length. Now, again, just write it out and you see that that is true. A dot A is the magnitude of A times the magnitude of A times the cosine of the angle between A and itself, which is 0 degrees, and the cosine of 0 is 1, so we indeed get A squared. And this can also be rewritten as A equals the square root of the dot product of A with itself. So we see that one way of calculating the length of a vector is by taking the square root of the dot product of a vector with itself. A final property that we need is that if we take the dot product of A and B and multiply that result with some arbitrary number lambda, we get the same result as we would have gotten if we had multiplied either A or B by the scalar lambda and then taken the dot product. Another way of saying this is that whenever you have a dot product and there is a number somewhere within the dot product, you can just pull it to the front. So that is everything we need about dot products. The third and final kind of product between vectors is known as the cross product. A cross B is a vector. That alone makes it completely different from A dot B. A dot B is a number. A cross B is an arrow. They are very different animals, so make sure you understand that difference. How is A cross B defined? Well, it's an arrow whose magnitude is equal to the magnitude of A times that of B times the sine of the angle between them. Remember that the angle between them lies between 0 and 180 degrees, and the sine of an angle in this interval can never be negative. That means that AB sine alpha is always a non-negative number, which is a good thing. If that could have been negative, it would be meaningless to say that it is the magnitude of something, the length of something. The fact that it cannot be negative makes it at least potentially sensible as the length of something. But this only gives us the magnitude of the vector A cross B. What is the direction of the vector? To understand that, let's take two vectors. B, I took it to point to the left. A points to the left upward parallel to the YZ plane. The direction of A cross B is defined as perpendicular to the plane formed by the two vectors A and B. The plane formed by A and B is the gray plane I drew now, and it is basically the plane of our screen. But there are two directions perpendicular to it. It can be perpendicular to it coming out of the screen towards us, the direction I drew in blue, or into the screen, away from us, the direction I drew in green. Which one is it? To know in which direction A cross B lies, we need something known as the right-hand rule. What it says is the following. There are two possibilities, out of the screen or away from us into the screen. Take your right hand and point your thumb in either one of those two directions. If I point my thumb away from me and I close the fingers of my right hand, or I point my thumb towards me away from the screen and I close my fingers, in one of those two cases, my fingers closed in the direction going from A to B along the arc I drew here. The direction in which my thumb points when my fingers close in the correct direction, that is the direction of A cross B. Now, because of the camera, which mirrors me, it may look weird to you, but try it yourself. Point your finger, your thumb of your right hand towards yourself, away from the screen, close the finger of your right hand, and what you will see is that your fingers close in counterclockwise direction, which is exactly the direction I want, given the figure in front of us. If on the other hand I wanted to calculate B cross A, I would have to again close my fingers, but going from B to A, so in clockwise direction. And that is the case, my fingers close in clockwise direction when my thumb points away from me. So B cross A points away from us into the screen, while A cross B points towards us out of the screen. Note that the difference, the order in which you write them, makes a difference. A cross B and B cross A are not the same anymore. So what are the properties of the cross product? Well, the first one is exactly what we just said. A cross B and B cross A are not equal to each other. They have the same magnitude, but they point in opposite direction. That means that one vector is equal minus the other vector. A second property is again a kind of distributivity. Basically, you're allowed to open up brackets when it involves cross products with sums. Thirdly, the cross product of a vector with itself is the zero vector. That follows simply from the definition of the magnitude of the vector. If I look at the magnitude of the vector A cross A, it is by definition equal to the magnitude of A times that of A times the sine of the angle between A and A, which is 0 degrees, and the sine of 0 degrees is 0. So we get a vector whose magnitude is 0, which is by definition the zero vector. And the final property is that if we take the cross product of A and B and multiply that result with some number lambda, we get the same result that we would get if we were to multiply either the vector A or the vector B by the number lambda and then taken the cross product. Again, what it says is that whenever there are numbers within cross products, you're always allowed to pull them to the front. The final thing about cross products is what is their geometric meaning. So to understand what it actually means, we know how to calculate it, but what does it represent? I will take two vectors A and B with an angle alpha between them. Using those two vectors, we can create a parallelogram. The question I want to answer is what is the area of this shape? Now, the area of a parallelogram has as a formula its base times its height. I choose as base the red line, which is simply the magnitude of A. For the height, I take the vertical dashed line I drew. Note that this created a right triangle. In this right triangle, I can look at the sine of alpha. Now, the sine of an angle in a right triangle is the opposite side divided by the hypotenuse, which is h divided by b. And that means that h equals b sine alpha. I now plug all of this into the formula for the area, and I find the base, which is the magnitude of A, times the height, which is b sine alpha. Now, ab sine alpha was exactly what we defined as the magnitude of A cross B. That means that the magnitude of A cross B is the area of the parallelogram formed by the two vectors. That is everything I wanted to tell you about the basic algebraic operations on vectors. In the next clip, we will look at the concept of components of vectors, how to work with them, and how to translate what we just did in this clip using those components. I'll see you then.